Hello everyone, and welcome to my video on random forests, which used to be my favorite algorithm until CapBoost took over. But I think random forest, the ideas of it are very important, especially in things like finance, where overfitting is such a big deal. So this is going to be a standalone video, which means you don't really need any prerequisites except maybe some prior knowledge on decision trees, which I'll cover in another video and link in the description. I'm going to talk about maybe some things that normal videos don't talk about. So I hope you enjoy. Also, this is part of my machine learning applied to finance series, but it's a standalone video, meaning you don't need the other videos for this one. But the data sets for this video build on data sets from those videos. And also, let's say you're an expert in random forest. I think this is also useful because eventually we're going to talk about tweaking random forest and things like that for things more related to stock market prediction, meaning we're going to change the Bootstrap sample. So anyways, I hope you enjoyed this video. If it's helpful, please like and subscribe. It puts a smile on my face. So anyways, decision trees, of course, are maybe the most beautiful algorithm there is. It's very cool. You know, you have a visualization. Let's say you're trying to predict if the stock will go up or down. You say, okay, if log return is less than this, and if some technical indicator is greater than that, you go through the tree, and then at the end you have buy or sell, or price will go up or down. The issue with decision trees is most phenomena are not that simple. So basically, if the tree is too small, you have underfitting and high bias, low accuracy. If the tree is too large, you have overfitting or high variance. So this is where random forests come to the rescue. So I just want to give you some background information. So random forests come from something called bagging, and before that, what's called the bootstrap technique. So what is the bootstrap technique? So let's say you have a data set of size, I don't know, like 10, for example, right? So what does the bootstrap do? The bootstrap takes a random sample of 10 with replacement. So let's say my 10 are labeled 1 through 10. I randomly select one of them, 1 through 10, and then I put it back in, 1 through 10, so on. So this will be my first bootstrap sample. As you see, it selected 4 twice, 6 twice, but it did not select 1. And you keep doing this, and let's say there's like some quantity of interest you want to estimate, like I don't know, like you want a distribution over the mean or whatever. So then you do this thing, you want like a confidence interval over the mean. So then you draw this thing, you take the mean of it, you keep doing the bootstrap, and then eventually you'll have a lot of samples, and then you can estimate the mean over that. So that's just background info. I don't want to get too much into detail. But okay, so then there's also bagging, which is called bootstrap aggregation, which is for variance reduction. So what happens is like you fit a model on a bootstrap sample. You have like n of these bootstrap samples, and then you take an average, and that lowers the variance of one individual model. Okay, and then random forest goes one step further. So let's talk a little bit about random forest. So it's from Bryman et al. He has a really cool paper here. Way long ago, he says cool things like random forests never overfit, all this interesting stuff that might not be true. But anyways, it's worth learning about. And actually, there's a book, The Elements of Statistical Learning, by this is like the Bible of statistical learning. And in this book, they actually talk a lot about his theories and what seems true, what seems not true. I highly recommend going through this book. It's actually online for free for many years. So if you Google, I don't know why Bing never shows it for me, but if I do Google and then I do Control V, I get the Elements of Statistical Learning PDF for free. Has a section on bagging, random forest, all that good stuff. And it's like the Bible of this stuff. Like this is really good book. And they have an even simpler one, but it uses R, so I refer you to the good one, to the more used one. Anyways, so what are random forests? So the idea is, so bagging, remember, was we randomly bagging was a way where we randomly selected a bootstrap sample So like selecting from our data set with replacement and fitting a model and doing that a number of times and taking an average. So this reduces the variance. But for a random forest, now you're going to have an ensemble, or like you're going to have many trees together and you're going to combine them in a way to reduce variance. So another issue of the variance comes from the fact that the trees could be correlated to each other even if you do the bootstrap sample. So so the fitted decision tree, usually it's like some sort of greedy algorithm where you like basically find what's the best split, what's the best split, what's the best split. So basically what can happen is you can still have many trees that are correlated. So the random forest adds this thing called a random subspace method. So like it'll let's say you have 100 features, that'll randomly select 10 features for the first tree, 10 features of the second tree, and so on. This is of course without replacement. And it'll fit the trees on this random subset of features, and this reduces the correlation between trees, and it helps with reducing the variance overall. So basically, to summarize the whole procedure, let's say you have a data set with n examples and f features, capital F features. For a certain number of trees, you sample with replacement n examples. This is the bootstrap we're talking about here. And then you you randomly sample without replacement. The first is with replacement, the n examples, and the second is without replacement, small f less than big F features. Then you fit your decision tree on that, and then you take an average for regression trees and an average of the probabilities for classification trees, and that's basically your final prediction. So for classification trees, when we take the average of the probabilities, we can then take the argmax. So basically, this is the majority vote, basically. But I like terming it in terms of probabilities because a lot of times you want to be able to customize it. Like let's say you're doing binary classification. If the probability is 0.51 and 0.49, you can say 0.51 is above 0.5, so it's class 1. Otherwise, class 0. But you can also make your threshold as 0.51. It's a small technical thing, but basically, big picture, it's like an average of the predictions. And if you really want for classification, it's a majority vote of the predictions. So this works by lowering the variance by combining many trees. And one other amazing benefit is this is absurdly parallel. So like since the trees don't depend on other trees, you can literally fit these models in the most parallel way. I can fit one on Earth. Someone can fit one on Mars. Someone can fit one on the moon. And then we can just combine it together at the end. So that's why things like Spark and a lot of the big data frameworks really use this type of stuff. And by the way, Sckit-Learn has a parameter for parallelization in terms of like number of cores you have. It's called n jobs. And you can set it to -1 to use all your cores or whatever number. But that's for another time. Anyways, and here's some documentation in Sckit-Learn. We'll talk about it. So let's just real quickly go through a walkthrough of this thing. And I kind of showed you guys this already, but like the algorithm is kind of like this. It's like you fit tree 1 using the random bootstrap sample, 790 whatever, and then using the random 3 selected features. You repeat this for tree 2, tree 3, etc. And then you average the tree's predictions to get a final prediction. And for classification, you can take the argmax or the majority class. Okay, so one important thing to note, and this is basically the whole algorithm, other than fitting the decision tree, which is another video. But notice one cool thing is not all training examples are used in every tree, right? So, so like we can actually do some math on this. The percentage of trees in which like an example is selected as n equals infinity, like what's the probability that you will what's the probability that you're going to I lost my train of thought. Okay, what's the probability that a particular training example is selected, it actually turns out to be when n is large, your training data set is large, and you have a ton of trees as that goes to infinity, it's going to be 1 minus 1 over e. Why is that? Because the probability of not selecting a particular I is n minus 1 over n. Is of not selecting a particular I is n minus 1 over n, and that equals 1 minus 1 over n, and that is the definition of e. And so 1 minus that is 1 minus 1 over e. And another way we can see this kind of empirically is like, let's say we define num trees to be 10,000, and n equals num trees, meaning our data set of size n. And let's say I'll keep a count. I'll start with 0, and then I'm going to randomly choose. Let me just write replace. Let me write everything out so it's more clear. I'll write replace equals true. Oops. So this is with replacement, and then I'm gonna basically like look at all the times a specific example is selected and count it, and average over the number of trees. So this is kind of an empirical validation of this, and you'll see that it's actually very close to 1 minus 1 over e, and that's like the theoretical value. Okay, so while this runs, I use some pretty big numbers, so it's sorry, my face is a little messed up. I'm not good with this background remover. I got to figure that out. So eventually this will finish, and it'll give you something that's very close to 1 minus 1 over e. In the meantime, we can do something like this. We can do like np.mean count over num trees, because it's going to be a vector for each example, minus 1 minus 1 over np.exp1. So we can just kind of see on average, and let's do np.abs. On average, what's our error between this? And we can, we can do an error rate on average. So we can do this minus this. It's like predicted minus actual over actual. And I guess I picked some pretty big numbers, so it's taking forever. This is like the average error. Okay, and what did I do wrong? My parentheses is in the wrong place. So you see, like, we have the error is less than 1%, which is good enough for me for this video. But anyways, it shows that like basically 62% of the time, sometimes you call the 62% estimator, that you select a specific training example. Okay, so this actually gives us a topic called out-of-bag predictions, which is kind of cool because in theory what happens is like, okay, let's show a simulation again. So you fit tree 1 with example 0, 2, 2, 2, 9, 8, 6, 1, 9, 2, but you can see that you did not fit on 3, 4, 5, 7. So what you can actually do is you can do like what's called out-of-bag predictions. Is basically, instead of doing like some cross-validation like k-folds or whatever, you can actually predict, you can basically only use trees that the model has not trained on. So basically, let's say I want to predict example 3, right? I can use tree 1, which does not use 3. I can use tree 2, which does not use 3. And I can use tree 7, which does not use 3. And I can use tree 8, which does not use 3. So I can use those 4 trees, and then I can make my estimate based on those 4 trees. So that's called the out-of-bag error, where you just kind of make a prediction using trees that the you make a prediction on a particular example just using trees that that did not use that example in training. So this is called the out-of-bag prediction. Okay, so right now we kind of see a huge problem. Okay, so in our previous videos, remember we talked about like triple barrier method and things like that. So we talked about the fact that our labels can have overlap and labels can be correlated. So let me see if I actually have it here. So, uh, okay, so okay, so like you see here, like let's say this is our labels. We see that the labels are correlated with each other. So if you're gonna do an out of bag prediction, it's kind of like messed up a little bit because you have some of the you don't select let's say you don't select example 2, but you have example 1 and example 3, so like you might have most of that information, so like it's going to overinflate your accuracy. So for overlapping, it's really bad. Another problem is, and this is where like you guys will need to see my next video on dealing with overlapping and the sequential bootstrap and that sort of thing. And this is much more related to like the finance stuff and the finance examples, because we're going to talk about like overlapping examples, concurrent examples, and stuff like that. But we'll talk about that in another video. But like basically the big picture is if you have overlapping examples, the trees are kind of going to be very, very similar. And the bootstrap is going to completely lose its effectiveness. And it's basically the variance reduction is not really going to happen as much as you really want. Okay, so with all this stuff out of the way, let's talk about like a scikit-learn example. Okay, so just real quick. Let's load a data set. This data set was created in my other videos. And I can, if you reach out to me, I can give you the data set if you just want it specifically. But the data set looks like this. I'm going to have basically all these technical indicators people use for stock market prediction. And I'm going to have a label, which is like buy or sell. And it has a sample weight because we talked about like sample weights in a previous video. And I'll show you how to use that. So basically, let's just kind of show you guys like how to actually do this in practice. So we're not talking about cross-validation and all that stuff. We're just kind of showing you a small example. And we're going to mostly do classification. And then at the end, I'll show you like a regression example, but it's pretty much the same. So what do we need? First, let's split our data into train test, just to show you guys something. So I split it into train test along time. Okay. So now let's say we want to do random forest for classification. So define RF for classification. So you can use sklearn's random forest function, which is basically from sklearn.ensemble import random forest. There's random forest classifier, random forest regressor. There's but we'll do random forest classifier, and we can fit the classifier like this. Random forest classifier. And n estimators is basically the number of trees. So let's just do 500. Max depth, and I'm giving you the most important parameters. So like I wrote them up here. Let me just go through it for just 2 seconds. Class weight is like a dictionary that you can say like, okay, I want to give the 0 class certain weight, 1 class certain weight, or you can do balance, which like overall will weight everything by the example size, or balance subsample, which basically does it in the bootstrap. It makes the bootstrap sample using weights. But balance just makes like you have a normal bootstrap sample, and then you have class weights, right? But the balance subsample makes the bootstrap sample itself consider the class weights. So let's say class weights are like 5 and 1, 5 for the 0 class, 1 for the 1 class. It'll give 5 times more likelihood to the one with the higher weight. And you do this because our data sets are not balanced, so it's very important. N estimators is the number of trees. Criterion, you can have like Gini, entropy. I'll talk about this a lot more in the decision tree video. Max features is a very important one. That's the number of features we want to randomly select for each tree. And the other features like the other parameters like max depth, max samples leaf, max sample split, max min weight fraction leaf, min weight fraction split. These are all from the decision tree. So max depth, of course, is the maximum depth. Min samples in a leaf means like you split your data set until let's say you have your leaf has let's say 9 examples. That's not good if you have a limit of 10. So you have to have a minimum amount in order to have this leaf. So it's a way of controlling the size or the overfitting. But for random forest, we tend to want to make it big. But we also do want to care about overfitting. And there's min samples in a split. So let's say you do not want to split. Let's say min samples in the split is 100 and you have 99 samples here. You're not going to make any more splits. And if you're using sample weights, these will be called min weight fraction leaf, min weight fraction split. We'll talk about this more in the decision trees. This is something that's actually extremely important. It's called max samples. So max samples is very important for overlap. The overlap thing we spoke about earlier. So it's one way to like make the overlap, make the trees less correlated. So max samples means like, okay, let's say your data set of size is a size n and you're selecting a Bootstrap sample of size n. Instead, maybe you're going to want to select a sample of n over 10 or whatever, a smaller sample. So this helps with overlap a lot. So that's good. So you can specify a fraction like 0.1 and then it'll do like n times 0.1, or you can specify the amount. Like you can just write like, let's say your data set is a size 5,000 and you write 2,000, it'll make max samples 2,000. And then there's a few other things. Let's say you want the out of bag score. You can set this to true. Random state is if you want to reproduce the result, you can set a random state. N jobs is the number of jobs. This is for parallelism. You can set it to -1 to use all your cores. By default, it's none, I think. So anyways, let's get started. Let's be practical. Let's talk about some of these things. Let's say we do max depth. We'll do 9. Class weight. Let's do balanced subsample. And let's do out of bag score equals true because I want to show you the out of bag score. And the fact that because this data set, I specifically chose the data set from my other videos when I was using the triple barrier method, and there's overlap between the examples. So I specifically know that the out of bag error is going to overestimate the performance. So let's do max features equals 0.1, and let's just do a few others. Min samples in split, let's do 10. And you know, that's good enough. So this is the random forest classifier, right? This is the definition of the classifier, right? So now let's fit the model. First we give it the features, and then we actually fit the model. So how do we fit the model? We can do CLF, let me write this here, fit the model. And you can specify the sample weight when you fit the model. So you have to do like clf.fit train feature columns. And these are all numeric. We'll show you how to deal with categoricals in other videos, but the label and this is how you fit it without the sample weight. But like if you want to fit it with the sample weight, you would do like sample weight equals train sample weight. Okay, so this is running. Because I did out of bag score equals true, it's going to take a longer time because this has to like evaluate the out of bag performance. But okay, the models fit, your random forest is fit. So the random forest, of course, is like a lot of these decision trees. So you can get the individual decision trees by doing clf.estimators, and then you get a list of these decision trees. So in particular, you could do like 10, for example, you get decision tree classifier. you can also get the parameters if you really want. So you can do get params. You can do clf dot get params. And what a lot of people like is you can get feature importance. The default feature importance is based on mean decrease in impurity. And Lopez de Prado's Advances in Machine Learning talks about it a lot. If you guys are interested in it, I'll also talk about it and make a video about it. But anyways, you can get feature importance by just doing clf dot feature importance. And to plot it nicer, you can combine it with the feature names. Feature names in. And I'll call this name. And then I'll call it score. Or clf.feature importances, and then we can sort the value by descending order. Equals false. So now you get the features in the right order. And then okay, so this is the interesting thing. Since we set out of bag score equals true, we can get out of bag predictions, right? So let's do that for a second. So if we do, so we can do clf that out of bag score. That gives us like the accuracy score. That's the default. It's 60%, which is way too good to be true. So let's just show you another thing. There's also like the clf.oob decision function, and this decision function kind of tells you like what probability to predict class -1, what probability to predict class 1. So basically we can use this to get a confusion matrix, right? So we can basically do like confusion matrix, and let's call this probs, the probability of predicting the second class. We'll do this thing, and we'll take the 1. Oops. I'll call it OOB props, out of bag props. And all these all these metrics are like, I wrote it here, like from sklearn.metrics, import confusion matrix, classification port, accuracy score, balance accuracy score. There's also like AUC score, all these other ones. I don't want to get into too much detail. I just want to show you guys the fact that the out of bag error is messed up because they're not independent. So like the out of bag error, I do the out of bag probs, and then let's make a threshold. We'll do like out of bag preds. We'll do np.where out of bag probs greater than or equal to 0.5, then 1, otherwise -1. And let's do a confusion matrix. We'll do train label and OOB preds. And damn, if you could predict like this, if you could get the this class right, 37 out of 37 plus 27, and this class right, 19 out of 19 plus 11, you're gonna be a billionaire. But unfortunately, it's because we had correlated examples and everything got messed up. So that's why it's overshooting. You can also look at it by looking at the log loss. So you can do log loss, train label, and out of bag props for log loss. And by the way, in my other video when I was introducing machine learning, I told you guys that the random guessing is 0.6931. Okay, so now okay, so that's one thing. You can also do the ROC AOC curve. I just want to show you guys. Oops. Train. So the AOC curve is about 60%, but you'll see that this is way too optimistic. Okay, so because of the overlapping labels, as I said like 5 times now, but now let's apply everything on the test set. So let's do let's call it test preds equals clf.predict test feature calls, and then you get if you just do the pred method, it gives you the actual predictions with a threshold of 1. So let's also do test probs, and we'll do clf.predict proba test feature calls, and then remember we get test probs like this, and then let's take the prediction of predicting 1, which is the second one. Okay, so using this we can do the accuracy score. Do accuracy score, test label, test preds. 49%. See, less than random guessing. Worse than this 60%. Okay, now the confusion matrix. The point of this was just to show you like the out of bag error being stupid in this case. Test label, test preds. You probably don't have patience for this, but see, the confusion matrix is pretty bad. You can do the log loss and the rock AUC score. The log loss is here. Log loss is oops, sorry. And the log loss is worse than random guessing. It's worse than 0.693, but not that much worse. And then you can do the AUC score, of course, rock AUC score. And 50% is random guessing. It's worse than random guessing. So you see that the out of bag in this case is not good. Okay, so I wanted to talk for a second about so this is using the random forest classifier class in the sklearn.ensemble, but you can also use the bagging class, bagging classifier class with the base estimator being the decision tree. So you can do from scklearn.ensemble import bagging classifier, and then from scklearn.tree import decision tree classifier. And then you can actually what you can do is you can actually manually do this. Is you can do random forest via bagging, and you give it the base estimator and then other parameters. This doesn't give you certain things like feature importance and that sort of thing out of the box, but it's basically another way to construct this random forest. You have the big bagging classifier, you have the base estimators, you can have the max features in max samples, things like that. So just another way to do it. Let's define the base estimator for a second. It could be like a decision tree like this, a decision tree classifier. This could be the base estimator. Okay, so this is the bagging classifier. So just for sake of completeness, we can also do regression. We could use the random forest regression regressor and the bagging regressor. So I'll just show you a case with random forest regressor. It's a little bit different. There's just a few different things let's say the splitting criterion might be a little different. We can use so let's just if you do help random forest classifier, you see the defaults and stuff like that. Splitting criteria is Genie, and you can have impurity, log loss, a few other ones. Max features, by the way, by default is square root because researchers found that was good for classification. But for regression, you have other defaults. You have forest. Just run one. I don't know why this. I don't know why the regressor takes forever, but random forest regressor. Forest regressor. You see that there's different criterion, and there's squared error, absolute error, Friedman, MSC, Poisson. The default is squared error. So anyways, I think this is so this is how you do the regression, and then you have similar parameters and that sort of thing. This is how you can do random forest regression. And here I had a data set where you have to predict the simple return. It's another data set. So I'm kind of rushing through this because the market's still open. I did num estimators as one. So let me make interrupt this. Let me make num estimator is 100 for a second, and then and n jobs equals -1 tells you to use all cores. But okay, while we're at it, I just want to talk about a few other things. So if you do, 1 second. Let's do extra decision tree classifier, sklearn. So if you look at the decision tree classifier for sklearn, you'll see that like there's criterion, Gini, entropy, log loss, and the default is Gini, and you have a splitter like a best and random. So by default, it uses the best thing, but sometimes actually using the random splitter for our case in finance is better, where we're gonna randomly choose a feature to split on. So just FYI for future videos, and then because then you get a cousin of the random forest called the extra trees classifier. So this will be in extra tree classifier sklearn. So this will be basically like a random forest, except the trees are chosen with like a random splitter. So this is the tree part, but there's also, it's stupid. They named it the same for both, but like for ensemble, you have like extra tree classifier, and basically this is just like all these random trees with random features used for splits, and you combine that. But finance, there's a ton of overfitting, so this actually does, in my opinion, work better than the actual random forest. So I'll make a separate video speaking about that. Let's see, by the way, if this is still running. It actually finished. And just for the sake of, okay, it finished. We don't need to get into details. I want to show you, in this case, because I'm actually predicting 5-minute returns, you'll see that the out-of-bag error is not overly optimistic because there's no overlap. But let's ignore that and talk about a few other things. So what I actually recommend is, a lot of times the documentation is not enough. You have to really, you really want to be able to like understand what's going on. So I recommend just using something like PyCharm or VS Code, whatever you guys use, and like doing from sklearn.ensemble import, like let's say extra tree classifier or random forest classifier, because then you can do Control B and you can like actually see the code, and you can really see what's going on. And you can see like the different things that are going on, because we're gonna use this a lot when we're gonna customize because like Lopez de Prado speaks about like sequential bootstrap as one way to solve the overlapping label problem, the concurrent label problem, the non-uniqueness. So we'll show you how to like basically create your own class, which will override some of these classes and do that. So anyways, this was a little bit rushed and a bit of a mess, but I hope you enjoyed. If you enjoyed, please like and subscribe, and see you in the next video. Thank you.